Hey everybody, today we're starting a new unit which is called Systems of Equations, and today I'll define for you what a system is and what does it mean to solve one, and specifically we're going to narrow in on a method called the graphing method for solving a system. To begin, let's just dive in right away and see an example of what is a system. So suppose I have a handful of 22 coins, and these coins are just pennies and nickels. I don't know how many of each I have, but I do know that they happen to add up to 50 cents. My question for you is, how many of each type of coin are there? Why don't you go ahead and hit pause and try to see if you can come up with a combination of pennies and nickels that might work. Well, let's see. Let's try a couple combinations. Maybe 10 pennies and 12 nickels. Would that work? 12 nickels, 12 times 5, that would be 60 cents. And 10 more cents, that'd be a total of 70 cents, which would be too many. So, how about 10 nickels and no dimes? That's 10 times, or no pennies. That's 10 times 5, that's 50 cents, right on. But it's not 22 coins. It looks like we have to somehow find something that is both 22 coins, yet also adds up to 50 cents. I'll spare you guys the agony, and I'll give you the answer. In this case, it's 7 nickels and 15 pennies. If you do 7 times 5, that's 35 total cents, plus 15 more cents. That would add up to 50 cents total. And 7 coins plus 15 more coins, that adds up to 22. Now, this is a great example of a system of equations illustrating two different constraints, or two different equations. The first constraint is the fact that I have to have exactly 22 coins. You'll learn later on that we can write that as an equation. The number of nickels plus the number of pennies has to add up to exactly 22. And the other constraint is that the total amount has to add up to 50 cents. We can write that as an equation as well. We would write 5 times the number of nickel, that is 5 cents per nickel, plus 1 cent for every penny, has to add up to 50. And our goal is to come up with a combination of n and p that makes both of these equations true. That's what a system is, juggling two different equations at once. So, here's a more formal definition. A system of equations is two or more equations that must all be true. Now, in Algebra 1, we'll stick to just 2 equations, but later on in Algebra 2 and in Pre-Calc, you'll easily start to study systems that have 3 or more different equations with 3 or more different variables. So, a solution, then, to a system is that it is an ordered pair of numbers that the variables can hold that makes every equation in the system true at the same time. Notice the vocabulary word, ordered pair. That's the XY combinations that you've seen before. So, solutions will be these pairs of numbers that have to make everything true at the same time. One of the primary skills you'll learn first is to check if a solution is a system to an equation. That's simple enough to do. You do that by substituting the numbers in for the variables and checking that it works everywhere. So, as an example, we'll go with the system 3x plus 2y is 4, and negative x plus 3y equals negative 5, and we'll try a couple pairs and see if they work. First, we'll try 0, 2. So, everywhere we see an x, we'll plug in a 0. Everywhere we see a y, we'll plug in a 2, and we'll see if this works. 3 times 0 is 0, 2 times 2 is 4, 0 plus 4 does in fact equal 4, so it works for that first equation. Negative 0 plus 6, 3 times 2, is 6, which does not equal negative 5, so, sorry, 0, 2 is not a solution. Next, we'll try 5, 0. We'll plug in a 5 for x and a 0 for y. And 3 times 5 is 15. 2 times 0 is 0. That does not equal 4. So 5, 0 is not a solution. I'm not even going to waste my time checking it in the other equation because it wouldn't matter. And finally, we'll try the combination of 1, 1. So I'll plug in a 1 for x and a 1 for y. 3 times 1 is 3, 2 times 1 is 2, 3 plus 2 is 5, which does not equal 4, so it's not a combination either. So how do we find the correct combination? Well, that's the key. We don't necessarily know what the combination of numbers is, and in fact, I can't even promise you that it's going to be nice numbers. They might be fractions or decimals, and so just guessing numbers and hoping they work is not a very efficient method. In truth, there's about 5 different methods that people often use for solving systems of equations. One is what we've just been doing, guessing and checking. And like I said, that usually isn't very efficient. And for some systems it's okay, but for most it's not going to work. Today we'll focus on the graphing method, which is simple enough. You graph lines, you see where they intersect, that's your answer. Next week we'll talk about the substitution method and the elimination method, which are 2 more fun algebraic solving sort of methods. And when you get into pre-calc, you will study a new method called matrix methods, and that is for primarily equations that have, or systems that have 3 or more equations. You probably wouldn't want to use it on a 2 by 2 system because it's overkill. It's taking a sledgehammer to a picture frame nail or something like that. So let's focus in on graphing and see how it works. So the first step in the graphing method is, as I mentioned earlier, to graph the equations. You can do this by either using y equals mx plus b ideas, I'm thinking of slope and intercept, or you can do this by plugging in some points. I like to find the intercepts, for instance, by plugging in zeros and plot those points, connect them with a line. Once you've got the graphs made, then you're looking for their intersection. So find the coordinates and ultimately test those coordinates, the xy combination where they meet, and see if it makes both equations true. That's the ultimate check to see if it works. So here's an example. 2x plus y equals 2, and negative x plus 3y equals 6. We'll start by making a graph of both of these. This first equation, 2x plus y equals 2, might be easy to rewrite in y equals form by subtracting 2 x's. That gives us y equals negative 2x plus 2. And as a reminder, we begin at 2 on the y-axis. So I'll put a point there. And then the negative 2 indicates the slope. That means we go down 2 and over 1, down 2 over 1, and so on. And you can see a couple different points. I'll connect those with a line. And now we have to graph the other one. I could rewrite this in y equals form, but because I'd have to divide by 3, it's going to give us some fractions. I'm going to try using the other method on this. To use the zeros method, I'm going to plug in a 0 for x and calculate that y would have to be a 2 to make this true. So I'll start by putting a point at 0, 2. Then I'll plug in a 0 for y and calculate what x has to be to make it true. This would have to be a negative 6. And so if y is 0, x has to be negative 6. That point is over here. And if I connect these 2 points with a straight line, or as straight as I can draw on this stupid computer, you can see that those 2 lines appear to intersect at the point 0, 2. That suggests that might be the answer. To know for sure, I'll take a 0 and plug it in for x up here, and a 2 and plug it in for y. 2 times 0 is 0, plus 2 does in fact equal 2, so far so good. Over here, we'll plug in a 0 for x and a 2 for y, and that gives us 0 plus 6 equals 6, and that works, and so our answer is indeed 0, 2. That's the graphing method. Graph the lines, find where they intersect. We'll look at one more example quick. In this particular example, I've got the equation x equals -3, and a lot of people get scared about this equation because it looks a little unfamiliar. Really, x equals equations are very easy ones to graph. You just need to remember that x equals draws a straight vertical line. So find -3 on the x-axis, 1, 2, 3, and draw a straight line through it. Then this equation is already in y equals mx plus b form, and so I can go straight to graphing. We'll put a point at 4, and then the slope is 2 over 1, and so that suggests our next point would be up 2 and over 1, up 2 and over 1, which is kind of going in the wrong direction. Let's go backwards, down 2 and backwards 1, down 2 and backwards 1, and so on. And at first glance, it looks like our point of intersection is at -3, -2. And to know for sure, we will plug in a -3 for x. This one doesn't have a y in it, and that's okay. We'll just ignore it. -3 equals -3. That's true. And then over here, we'll plug in a -3 for x and a -2 for y. On this side, -6 plus 4 does in fact equal -2, and so -3, -2 is our solution. So that's the graphing method. So long for now, until next week when we talk about substitution.